Hello, welcome to today's algebra lesson. Algebra for the SAT, let's get started. So the first thing we want to talk about is evaluating an expression. An expression is an algebraic collection of terms collected together with math stuff. The main thing to notice is that doesn't equal anything. So we can't solve them, but we can what's called evaluate them, which means putting in a number for the variables and finding out what it means. So looking at that first one, what is the value of the expression 10x minus 4 over x minus 1 when x is 7? We're going to go ahead and make x 7 and see what it equals. So the first thing you're going to do is copy out the expression. Copy out the expression. Let me get a bigger pencil there. Copy out the expression, but instead of the x, you're going to put parentheses. And this is going to keep you nice and safe with your signs, and you're going to enter it into your calculator just like this with the parentheses. We're going to put in a 7 for where the x's were, and then we can go ahead and punch that out in our calculator, and we're going to get 7 times 10, that's 70. Minus 4, which is 66 in our numerator. And our denominator, 7 minus 1, that's 6. Divide by 6, and we'll get 11. That's what the value of the expression 10x minus 4 over x minus 1 when x is 7. Now for this next one, we have if a equals 3 and b equals negative 4, and c equals 8, what is the value of AC minus AB? I'm going to shrink this down a little bit, give us a little more space. Let's try that again. Okay. So again, we're going to copy out our expression with parentheses where our numbers are going to go. And in for our A, we'll go 3. That'll go here and here. In for our B, we'll go negative 4. Negative 4 will pop right in there. And in for our C, we'll go 8. So for our first guy, we have 3 times 8, which is going to be 24. Now you'll notice here the double negative, which makes this a plus 12 for 36 as our answer. Now the next question asks, what is the value of a right circular cone whose base has a radius of 3 and whose height is 10? Now everybody wants to freak out about this question because, oh my goodness, it's geometry. But please remember, the formulas that you need for the geometry are in the reference on the upper right hand of your testing screen. Click that reference and you'll see the formula for a right circular cone. So if we're going to go grab it right here, let's just go grab it from one of our drills here. If we go to the math on resolve, we can just go grab any drill here so you can kind of see it. We'll go for our basic algebra drill. Click on the reference in the upper right hand corner and we'll see where our reference sheet is. Now a right circular cone will be on the bottom row with the circular base, and you'll see there's a circular base and a pointy top, and our formula is the volume of it equals 1/3 pi r squared h. So we're going to go ahead and pop that right into our paper, right? Volume equals 1/3 pi r squared h. And again, we're going to go ahead and put parentheses for the things that we're going to evaluate. We're going to put a 3 in for our radius. So they say we have a radius of 3 and a height of 10. We're going to put a 10 in for our height. And we're going to see that if we punch this into our calculator, I would recommend, usually they don't multiply the pi through. We'll put this, and this into our calculator, and we'll get 30. So V equals 30 pi. So not so bad, just the same, right? So again, when you're extracting this, make sure you write down on your paper R equals 3, H equals 10 onto your scratch paper, so that way when you write down the formula, you can see where they go. Now, let's do some practice. If x equals 5 and y equals 4, what is the value of 3x minus 4y? We'll do 3 times 5 minus 4 times 4. So that's 15 minus 16, or negative 1. For the next one, if x equals 3 and k equals 12, what is the value of x squared plus kx plus 6? Well, in for our x will go 3, in for our k will go 12. So that'll give us 9 plus 36 plus 6. And when we add all those guys together, we should get 51. That's our answer. Now for the last one here, we have a equals 3b plus 4c over 2 when b equals 6 and c equals 10. Sometimes it's fun to just erase the b and replace it with what b is, and erase the c and put in what c is. So then when we evaluate that, we have 18 plus 40 over 2. So that's going to give us 58 over 2, or 29 for our answer. Now we have something a little more interesting. We have if j equals 6 times k times m minus n, what is the value of j when k is 100, m is 2, and n is negative 10? Again, let's make sure we're writing our parentheses. You'll see why, especially when there are negatives. You'll see what happens here. Put 100 in here, we'll put a 2 in here, and a negative 10 in here. Ooh, you can really see that double negative. So we see j equals 1200 plus 10, for 1210 is our answer. Now for this last one, what is the value of 8x minus 9 over x when we make our x 1/2? Well, 1/2 times 8, that's 4. 4 minus 9, that's going to give us negative 5 in our numerator. And we're dividing that by 1/2. Remember, dividing by 1/2 is the same as multiplying by the reciprocal. So that's the same as negative 5. Well, I'll write it out. Negative 5 divided by 1/2 is the same as negative 5 times 2 over 1, or 2, which gives us negative 10. Now, solving linear equations will mean an expression that now we've added an equal sign. That's what makes it an equation. You can solve an equation by getting the variable by itself on one side of the equation. That means we have to kind of undo everything so everything moves to the other side of the equal sign. So you can do this by doing the opposite of anything you see on both sides of the equation. So here, when we're looking at this, you want to remember, you want to isolate your variable term first by getting rid of anything that's on the same side of it, and then isolate your variable from the variable term. So the first thing we're going to do for this problem is copy it down onto our scratch paper. Showing your work is very important on this test. And because we want to isolate our variable term first, we're going to subtract 5 from both sides, and we'll get 3x equals 18. Then we're going to isolate our variable, undoing multiplying by 3 by dividing by 3. The 3's will cancel out, and we'll get x equals 6. Now this one can be a little bit trickier. We'll have the square root of x minus 3 over 2 equals 4. And now if we want to solve for x, again, we want to make sure we isolate our variable. But right now, the whole side, what's being done to the whole side? The whole side isn't having a square root taken of it. The whole side isn't being subtracted by 3. The whole side is being divided by 2. So we're going to tackle that first and undo dividing by 2 by multiplying by 2. The 2's will cancel out on the left-hand side, because really we're multiplying by 2 over 1. So if 1's in the numerator, 1's in the denominator, they'll reduce, and we'll be left with rad x minus 3 equals 8. We can then square both sides to undo the square root, and we'll get x minus 3 equals 64. We can add 3 to both sides, and we'll get x equals 67. Now you might be thinking to yourself, but Donna, my algebra skills might not allow me to do that. Well, there's a backup plan. Let me show you. If you're struggling with the algebra on this problem, you can use Desmos to help you. So go ahead and click on your calculator, and when we see it, we can enter our equation. So here you'll notice the only thing in there is x. So when we solve for x, we get a value. We get x equals 67. Now, if we were to graph x equals 67, well, that's just a simplification of what we have here, right? And we solved for x. When we graph the line x equals 67, we get a vertical line at 67. So look what I can do. I can enter this into Desmos, making sure I use my parentheses around the numerator and denominator if I have anything interesting up there. Close my parentheses, and I'm going to divide that by 2 and say that it equals 4. Now when I zoom out, what you'll notice when I go over, I'm going to zoom out, zoom out. See, I have a vertical line there in red. When I zoom in on it, I can see, you know what? That vertical line hits the x-axis at 67. And that's how I know what my solution is, where the vertical line hits the x-axis, or where the vertical line is on the x-axis. So that'll be a great backup plan to help us if we're having trouble solving for x. Now, sometimes we'll have to solve for x in terms of y. So give a read for this question. It says, if y equals 5x plus 3, what is x in terms of y? Well, what they're asking us to do there is to find x, right? They're asking us, what is x? But they're asking us to find it using the language of y. So how will we do that? We'll go ahead and copy down our equation, and we're going to isolate our variable term just as we did before, and then we're going to isolate our variable within that term. But we're not going to get a number. When it says in terms of y, we're going to get an expression for x, something that has y inside it. So we'll subtract 3 from both sides. We'll get y minus 3 equals 5x. We'll divide both sides by 5, and notice what we get. X equals y minus 3 over 5. And because these types of questions very often are asking us to relate together two unknowns, in this case x and y, this is an excellent opportunity to use your plugin. If you put in an x and get out a y, that same relationship should hold true for the answer choices. So say, for example, I'm just going to pretend like, oh, this is answer choice A. Let's see if it works. If I put in a 2 for my x, and I say, okay, x is 2. Notice 5 times 2, that's 10. Plus 3, that's 13, which makes my y equal to 13. Now, if I put that into the right answer choice, this guy right here, it should work. So let's say, it says our x is 2, and that equals what our y is, 13, minus 3 over 5. Let's see if it works. 13 minus 3, well, that's 10. 10 divided by 5, that's 2. It works. So again, you can use plug-in on the original equation to find the relationship between your variables and then pop them into the answer choices to see which one expresses that same relationship. So let's do some practice. I will use Desmos for a few of these just to show you how it's done, but for the most part, we'll be solving these algebraically to get a little practice. So here we have, if 4 plus quantity a minus 4 equals 9, and we want to solve for a, well, notice that this is just an addition sign here. So when we distribute it, it's not going to change the sign on anything that's inside. So we'll still end up with 4 plus a minus 4 equals 9. We'll combine like terms. Negative 4 and positive 4 are both constants. And if I do 4 minus 4, they'll cancel each other out. And I'll get that a equals 9. That's for our first one, right? For our second one, we have if 5x plus 6 over 6 equals 11, we want to solve for x. We'll get rid of the 6 in the denominator by multiplying both sides by 6 in the numerator, or multiplying by 6 over 1. If I put the 11 over 1, I'll see what's going to happen on that side. On the left-hand side, the 6's are going to cancel out, and I'll be left with 5x plus 6 equals, now here there's just 1's in the denominator, so I don't have to write that, but the numerator is 11 times 6, or 66. We can subtract 6 from both sides. We'll get 5x equals 60. If we divide both sides by 5, we get that x equals 12. So because that was rather a chunky problem, let's try that one on Desmos and make sure that we get the same thing. Why is it not getting smaller? Let's try that a little bit better. There we go. Okay, let's try that on Desmos. I'm going to go ahead and split our view here. Okay, and let's type it in. Let's see what we've got. It's being persnickety. Let's try that again. Okay. You know what? I'm going to close this down, and let's go ahead and grab Desmos instead. Let's grab Desmos instead. Okay. So we're going to do 5x plus 6. If you forget to enter the parentheses at the beginning, you can always enter it at the end, just like I did. Divided by 6, use your little right arrow to go out of there, equals 11. And when we look at our graph, oh, do you see that little red line? Where did it pop up? It popped up at 12, which is exactly the answer that we got when we did it algebraically. All right, let's try our next one over here. Get rid of Desmos for now. We have if 4u plus 11 equals 3, we're going to isolate our variable term first and then isolate our variable within it. So we'll subtract 11 from both sides. We'll get 4u equals negative 8. We'll divide both sides by 4 to undo multiply by 4, and we'll get u equals negative 2. Now, there's no excuse for getting an algebra question wrong, because if u equals negative 2, you should be able to put the negative 2 back in there, and it should work. Pop it in your calculator. Is it true that 4 times negative 2 plus 11 equals 3? And it does, so we know we did it right. Now, looking at this next one again, let's clear our denominator. If 12x plus 4 divided by 4 equals 12, then I should be able to clear that 4 to undo dividing by 4 by multiplying by 4 over 1. 4 over 1, I'll put the 12 over 1 so it doesn't feel lonely. The 4's will cancel each other out, and we'll be left with our numerator. 12x plus 4 equals 48. If we subtract 4 from both sides, we'll get 12x equals 44. And if we divide both sides by 12, we'll get x equals, well, let's divide top and bottom by 4. Let's reduce top by 4 and bottom by 4. We're going to get something a little bit ugly, but that's going to be 11 over 3. No problems there. It's still a number. Up a little bit so we can tackle our next one. Now you'll notice here we have variables on both sides. We're going to make sure we combine them all on one side so we isolate our variable terms. So the first thing I'm going to do is subtract 4 from both sides. What that'll allow me to do is keep my constants positive. So it'll give me 9 minus 3z on my left-hand side equals 15z on my right-hand side. I'll then go ahead and add 3z to both sides, and you'll notice it cancels it out from my left-hand side and combines it with my z on the right-hand side, so I get 18z. We'll divide both sides by 18. How tempting was it to divide by 9 and get 2, right? But the 18s will cancel each other out, and we'll get z equals 1 over 2. And again, if you're wondering if this is right, go ahead and pop it back into your original equation, and you'll see that it is. Now for our next guy, ooh, this one's spicy. We have a variable in the denominator. We're not going to treat it any differently. If 3x over x plus 5 equals 4, we're going to go ahead and multiply both sides by our denominator, x plus 5 over 1 on both sides, x plus 5 over 1. The x plus 5's will cancel each other out, and on the left-hand side, we'll be left with 3x. On the right-hand side, don't forget to distribute your 4 to both of the terms that you multiplied it by, so we get 4x plus 20. We're going to subtract 4x from both sides, and that will help us combine our variable terms. They'll cancel out on the right-hand side, and we'll be left with negative x on the left-hand side equals 20. We can divide both sides by the coefficient here, which is negative 1. And that'll leave us with x equals negative 20. Now this next one looks a little spicy, but really we're just adding fractions together, and we know how to do that. We have 8 over x plus 2 over 3 equals 5. Now we have some options here. We can do the same thing by isolating our variable term by subtracting 2 over 3. So we can try that to start. So if we put 5 with a common denominator of 3 would be 15 over 3. So if I subtract 2 over 3 from both sides, it gives me 8 over x equals 15 minus 2, that's 13 over 3. And now that I have a fraction that equals another fraction, I can cross multiply. 8 times 3 will give me 24. equals 13 times 3, which is, rather 13 times x, which is 13x. We can divide both sides by 13, and we'll have x equals 24 over 13. Yuck! Should we see another way to do it? And go ahead and move this on over, make it nice and small, and give us tons of space to do something else. So, as I said, we could start by simplifying the left-hand side and taking 8 over x plus 2 over 3 and adding them together. Well, we'd have to get a common denominator, which in this case would be 3 times x, or 3x. So in order to get that here, I have to multiply the bottom by 3 and the top by 3, because multiplying by 3 over 3 is the same as multiplying by 1, which keeps things the same, changing their form without changing their value. Over here, I'm going to have to multiply the bottom by x and the top by x, and again, x over x equals 1, so changing the form but not the value. So our numerator over here, we get 24, and our denominator 3x, plus 2x over 3x. And when we put that together, we get 24 plus 2x over 3x equals 5. We can multiply both sides by 3x to clear our denominator. And what will we get? We'll get a little running out of room. So let's go ahead and try this here. The 3x will cancel each other out here. We'll be left with 24 plus 2x equals 15x. We can subtract the 2x from both sides. We'll get 24 equals 13x. Dividing both sides by 13, boop, boop, we're going to get that x again equals 24 over 13. Let's shrink that down, give us a little more room. Okay. For our next question, we have if p equals 5 times the quantity a plus 6, what is a in terms of p? Notice we're looking for what is a, so we want to isolate a. A couple ways to do this. If you thought to distribute first, you can absolutely do that, distributing the 5 to a and to the 8. We'll get p equals 5a plus 40. We could isolate our variable term and then isolate our variable from within it, subtract 40 from both sides, and what we'll end up with then is p minus 40 equals 5a. We can now isolate our a by dividing both sides by 5. The a's will cancel, and we'll notice, the 5's will cancel. See, the 5's will cancel, boop. And we'll be left with a equals p minus 40 over 5. A equals p minus 40 over 5. We get an expression, and that's why it's in terms of p. Now, if we want to see another way to do this, I'm going to go ahead and erase. If we want to see another way to do this, what we can do is decide not to distribute the 5 and see what happens. So if we have p equals 5 times a plus 8, we can begin just by dividing by 5. The 5's will cancel, and I'll get p over 5 equals a plus 8. We can subtract 8 from both sides, and we can get p over 5 minus 8 equals a, which is the same as what we had before, really, because if you'll remember, when we distributed the 5, we had p minus 40 over 5 equals a, and if I distribute the divide by 5 to both terms in my numerator, I'll get p over 5 minus 40 over 5 equals a, and 40 over 5, well, that just reduces to 8. So that's, again, same as what we had when we started without distributing the 5. All right, let's look at our next guy. If 2 over 3x minus 6 equals y, what is x in terms of y? We want to find out what x is. No big deal. We're going to have to isolate our variable term and then isolate our variable. So what is the first thing we're going to do? We're going to add 6 to both sides. Let's add 6 to both sides. And we're going to get 2 over 3x equals y plus 6. Now, the fastest way to get rid of 2 over 3 is to multiply by 3 over 2 on both sides. Multiply by the reciprocal. The 3's will cancel. The 2's will cancel. We'll be left with x on our left-hand side. And on our right-hand side, when we distribute that 3 over 2, we're going to get 3 over 2y plus 9. Now for this last one, I know it might look intimidating with all those variables, but all we're doing is isolating b in terms of a, c, d, and e, which will be on the other side. So let's copy down our equation. AB over CD equals E. Now again, we're going to try to isolate B, which means we're going to clear our denominator. We're going to multiply both sides by CD over 1. I'll put a little 1 under here so the E doesn't feel lonely. The CDs will cancel out and we'll be left with AB on our left-hand side. And on our right-hand side, E times C times D. And we'll divide both sides by A to isolate our B. And we'll get that B equals ECD over A. Now, just a little reminder about dealing with fractions. If you ever have a fraction times a variable, we have a couple options here. We can do 2 over 3, and we could think about that as times x over 1 equals 10. Multiply our tops together, multiply our bottoms together. 2x over 3 times 1, which is 3, equals 10. And then we have other options. We could put 10 over 1 and cross multiply, or we can multiply both sides by 3 to cancel that out here, and then divide both sides, and we'll have 2x equals 30, and then we can divide both sides by 2 and get x equals 15. That's one option. Not my favorite option. I'll tell you what my favorite option is. My favorite option would be to do it all in one step. So if you have 2x divided by 3 equals 10, multiply both sides by the reciprocal. That'll cancel out, especially if it's only a single term. If there was something else you'd have to distribute the 3 over 2, maybe that wouldn't be a great move. But right here, we're going to cancel out the 2's, cancel out the 3's. Notice we get x alone in one move. So x equals, and again, this is something you can punch into your calculator to get 15. Now, if there's a variable in the denominator, you can still clear the denominator by multiplying both sides by x. The x's will cancel out here. You'll get 18 equals 6x, and then divide both sides by 6 and get that x equals 3. Now here's a fun move. If you want to take 18 over x and set that equal to 6 over 1, you can cross multiply, right? But please know, whenever you have a fraction that equals another fraction, you can swap your diagonals and it will be an equivalent equation, something that's also true. So if I swap my 6 and my x, notice I get 18 over 6 equals x over 1, which is just x. Oh, look, one step and we're there. X equals 3. So that's always a fun little trick. All right. Clearing fractions. If there's just one fraction, isolate your variable term that has the fraction in it first. As always, you're going to subtract 3 from both sides and get 1/2 x equals 2. And then again, to clear 1/2, we're going to multiply both sides by 2 over 1, or 2. And we'll get that x equals 4. Now, if there's a few, you can actually clear all of them at once by multiplying by a common denominator. So if I say, what is the solution to the equation 1/2 x plus 1/3 equals 1/5? We can multiply the entire thing by 30 because 2 go and 3 and 5 all go into 30. An easy way to find that number 30 is just to multiply all the denominators together. And then we can distribute it to each term. 1/2 times 30 is 15, so that'll give us 15x. 1/3 of 30 is 10, equals 1/5 of 30 is 6. And again, you could do all that in your calculator. Subtract 10 from both sides, we'll get 15x equals -4. We'll divide both sides by 15. And we'll get x equals -4 over 15. And I do get the question a lot, Donna, can't I just subtract 1/3 from that side and then multiply by 2? Absolutely. If you don't mind working with fractions, you work with them. But if you really don't like working with fractions, and I think a lot of people don't, that's a good move to do to clear them. Now watch out for the mad slasher when you're adding or subtracting fractions. In order to cancel out a factor out of a fraction, something has to be a factor of the whole numerator and the whole denominator. So if we're looking at something like this guy here, you can see that 2 is a factor of 6x and it's a factor of 4. So when I factor it out, basically undistributing it, you can see they're the same because if I multiplied the 2 times both of these, I would get this guy, right? I factored a 2 out and then I can reduce it. We do this with numbers all the time, right? If I have 6 divided by 3, the reason it reduces is because 6 goes into 3 2 times. 6 is just 2 times 3. So when it's divided by 3, the 3's cancel each other out, and I'm left with 2. However, if I had the situation where I had, two terms like 5 plus 6 divided by 3, well, that's 11 divided by 3. It doesn't go in evenly, and the reason for that is 3 doesn't go into 5. 3 is not a factor of the whole numerator. It's just a factor of the 6. Now, some sneaky people will say, well, just reduce it, that's 2, so the answer is 7. No, it's not. It's 11 over 3. So don't be sneaky like that. That's called the mad slasher, and we won't have it. Now, here's an example of doing that with algebra. 2x over 6 divided by 6. We're like, ooh, I see a 6 and a 6. That'll reduce to 1. Haha, 2x plus 1. No, that's not a good idea. Do not do this. Much, much better. You can split the denominator, or rather you can distribute the denominator to both terms in the numerator, to this guy and this guy. So we get 2x divided by 6 plus 6 over 6. Because really, when you look at this guy over here, it's not just the 6 that's divided by 6. It's not just the 6 that's divided by 6. The 2x is also divided by 6. So we can show that by doing this and then reduce. This guy does reduce to 1, but this guy doesn't reduce. We can take 2 as a factor out of both and reduce it to 1/3. That's what we can do. So you can see this guy is not the same as this guy, so don't make that mistake. Now, when we're combining like terms, please remember this fun fact right here. Let's take a little look at it. I know it looks scary when it's written like this, ax plus or minus bx equals quantity a plus or minus bx. But really all we're saying is this. Say I have 3x and I'm adding that to 4x. How many x's would I have? Well, I would have 7 x's. And the reason that is if I factor an x out of both of these, undistribute an x from both of these, I'll be left with just numbers that are like each other and they can combine. So I'll have x times 7 or 7x. So that's basically what they're showing. Do you have to do this step every time you combine like terms? Absolutely not. But that's the paperwork behind it. So let's look at it over here. If 2x minus 4 equals 5 minus x, what is the value of x? We're trying to find x. Again, you can totally pop this into Desmos, but here's another option for you. If we add 4 to both sides, we can combine our constant terms. We'll have 2x equals 9 minus x. And then I want to combine my variable terms, get them on the same side. So do you see how I have one on my left and one on my right? We'll combine them by adding x to both sides. And notice here, I did the additive inverse. I canceled it out. So I'm left with 9 on this side and 3x, because I add the 1 and the 2 together. 2x's plus 1x gives me 3x. And I'll divide both sides by 3. And I'll get that x equals 3. Now, please remember distributing. It's one of the SAT's favorite tricks. If negative 2 times the quantity x minus 5 equals 1, what is the value of x? So we're looking for x. Again, you can pop this into Desmos or take that negative 2 and distribute it to both terms, right? Negative 2 times x and negative 2 times negative 5, we know we will get positive 10 equals 1, because a negative times a negative is a positive. Let's subtract 10 from both sides, and we'll get negative 2x equals negative 9. Divide both sides by negative 2, and we'll get x equals negative 9 over negative 2 gives us, the negatives will cancel each other out, and we'll get 9 over 2. Now, if you're like, Donna, why did the negatives cancel each other out? Well, you can think about negative 9 as negative 1 times 9, and negative 2 as negative 1 times 2. And tell me about negative 1 over negative 1. It just reduces to 1, so we're left with 9 over 2. Now let's combine distributing and combining like terms for a very tricky problem here. In the expression 3 times quantity 2x squared plus px plus 8, minus 16x times quantity p plus 4, p is a constant, which just means it's a real number that we don't know what it is yet. This expression is equivalent to the expression 6x squared minus 155x plus 24. What is the value of p? So if we're looking for that, you guys might remember this problem from the plug-in or back solve drills, because absolutely you can go ahead and just pop in the answer choices for p and see which one gives you the right thing. But we also know that these things are equivalent. 3 times 2x squared plus px plus 8 minus 16x times p plus 4, we know that that equals 6x squared minus 155x plus 24. So let's see if we can get the left-hand side to look the same first by distributing. We're going to distribute the 3 to everything, and we're going to get 6x squared plus 3px plus 8. Now remember from our math fundamentals discussion that you always put the number first, the constant second, the variable third. This will help you identify like terms even better. Let's distribute this negative 16x. So we'll get negative 16px plus 4 times negative 16x gives us negative 64x. Now, let's set that equal to our 6x squared minus 155x plus 24. And let's simplify our left-hand side. Our squared term doesn't have any like guys to combine with, so we'll just leave that as 6x squared. Our I feel like I dropped something. Yes, I did. Oh my goodness, did anybody catch my error? The 3, I neglected to distribute to my 8. Oh boy, that makes it 24. Don't be like me, okay? So now we'll copy out the rest of it. We do have a few x terms. We have this guy, and this guy. So let's write them all together. We have plus 3px minus 16px. Those are like terms. They have the same variables, the same constants, so we can actually put those together. That's going to be negative 13px minus 64x. And then we have our final constant plus 24, and that's what equals 6x squared minus 155x plus 24. Now we can combine our like terms by subtracting 6x squared from both sides, cancel out on both sides, and on the left-hand side we'll be left with negative 13px minus 64x plus 24 equals negative 155x plus 24. A lot of people, when they get rid of this, will forget that there's a negative here. This becomes 0 minus that, so we have to take our negative with us. So now let's subtract the 24 from both sides. You see how we have that same thing on both sides? They're going to cancel each other out. So we'll be left with negative 13px minus 64x equals negative 155x. Okay, well, look, see, I have the x terms here and here. Let's combine like terms. Let's add 64x to both sides. We'll get negative 13px equals negative 155 plus 64, which is negative 91x. Now, if I want to solve for p, I have to get rid of the negative 13 and the x. So we'll divide both sides by negative 13x. These will cancel, and we'll find out that p equals, well, these x's cancel, whatever negative 91 is divided by negative 13, so that negatives will cancel each other out, and we find that p equals 7. Now, if you're very savvy for this type of question, what you might notice is when we're up here at this stage right here, you might notice that these lovely guys over here cancel each other out by, in fact, I'm going to erase them. You might notice that these 24s cancel each other out. Let's erase them. And that now we only have our linear terms left. I'm going to erase this to give me a little more space. Now we only have our linear terms left, meaning the terms that have the x to the 1 on them. If that's the case, I can go ahead and factor an x out of both of these. factor an x out of both of these and be left with negative 13p minus 64. Quantity times x minus 155x. I can divide the x's out at this time. Boop, boop. And I'll be left with negative 13p minus 64 equals negative 155. I can add the 64 to both sides here and then divide by negative 13. Anyways, if that's your style, feel free. So we have options. Now, sometimes we have the very cool trick of being able to solve directly for an expression. See here, if 2x plus 1 equals 5, what is the value of 8x plus 4? Well, please notice, if I have 2x plus 1 equals 5, there is a relationship between 2x plus 1 and 8x plus 4. 2 times 4 is 8, and 1 times 4 is 4. So if I take the entire left-hand side and multiply it by 4, I can balance that by doing the entire right-hand side times 4 as well. If I distribute the 4 on the left-hand side, I get 8x plus 4, the thing I'm solving for. And on the right-hand side, 4 times 5, that gives me 20. So I went directly for my answer. Could I have solved this for x and then popped that x that I got in here? Absolutely. Could I have popped this in Desmos and found out what x is and then pop that in here? Absolutely. So we have lots of options. Now, if we solve linear inequalities, inequalities have not an equal sign, but they would have something that looks like an alligator mouth, going this way or this way. When we have the alligator mouth, as I call it, it's called an inequality. The alligator mouth is very hungry, and it always eats the bigger one and points to the smaller one. So if I say x, alligator mouth 3, that means x is bigger than 3. If I switch the direction, now the alligator is trying to eat the 3, so the 3 is bigger than the x. Technically speaking, it's not an alligator, it's a direction on the number line. If I'm pointing to the right on the number line, I'm getting bigger. And if I'm pointing to the left on the number line, I'm getting smaller if I'm heading in this direction on the number line. So really it's saying that it just means bigger and smaller, but I think thinking about it as an alligator mouth is a classic way to help you remember what this means. So let's talk about the algebra of it, yes? What values of x satisfy this inequality, 2x plus 1 minus 5? The trick is to solve it just like a regular equality, but if you multiply or divide by a negative, you need to flip. Here we're not going to need to. We'll just subtract 1 from both sides. We'll get 2x is greater than 4. We'll divide both sides by 2, and we'll get x is greater than 2. Success! We're done. Now for this guy here, what value of x satisfies the inequality negative 2x plus 1 is greater than 5? If I subtract 1 from both sides here, I'll get negative 2x is greater than 4. But now in order to isolate x, I'm going to have to divide by negative 2. And when I multiply or divide by a negative, I have to flip the direction of my inequality. So I'll end up with x is less than negative 2. Now, what if now I have a linear equation with 2 variables? This is a bit different because before we had, say, this linear equation 2x plus 5 equals 1 with just one variable. And when this happens, we can solve for x. I call this celebration station. Why? We have one variable, and if we have one equation and one variable, we can solve. If I have something like this, 2x plus 5y equals 1, I can solve for x in terms of y or y in terms of x, but I can't actually find a value for x and y because depending on what I put in for x, it will cause y to be something different. So, for example, in this problem, we say when x is 3. So I'm going to go ahead and make x 3, and that will determine what my value of y is. So here I'll have 6 plus 5y equals 1. Subtracting 6 from both sides, I'll get 5y equals negative 5. Divide both sides by 5. I'll get that y equals -1 in this situation. Now, if x was something different, so would y be. So keep your eye out for linear equations with two variables. Also notice if they didn't give us this, we wouldn't be able to solve for y. There wouldn't be enough information. So please remember, if you have one equation, you could solve for one variable, two equations, two variables, three equations, three variables, and so on. Now, I want to just stick in here a little reminder about the difference between a constant and a variable. A constant is a number that is represented by a letter, but it's just because we don't know what the number is. The variables, something like x and y, are represented by a letter, but we don't try to figure out what they are, because when they're in an equation together, both x and y, whatever the x is determines what the y is. So they're related to each other, they're dependent on each other, and they vary with each other. So it's not like it's going to be the same for the entire problem the way a constant will. A good example of that is in the equation y equals mx plus b. M and b are constants because no matter where you are on the line, the y-intercept is always in the same place. In this case, it's always 3. And the slope is always 2. We always go up 2 over 1, up 2 over 1. No matter where you are on the line, the slope is always 2. However, when I'm right here, my x value is 0 and my y value is 3. When I'm over here, my x value is 1 and my y value is 5. Depending on where I am on my line, my x value and y value will change. So just keep that in mind as we move forward. Because now we're going to talk about creating and understanding linear equations. Because sometimes you'll be asked to produce and sometimes solve linear equations from word problems. So being able to make an equation that you can solve is really helpful. Now, other times you'll just be asked to understand the parts of the linear equation. So let's talk about both. When we're given a word problem and we want to create a linear equation from that word problem, we can use some of those skills we use for our percent translation chart to help with translating really any kind of word problems. Whenever you see the word is, it means equals, of means multiply, per means divide, more or less, greater or less means add or subtract, respectively. Is greater than or is less than, whenever they add the is to that, that means we're going to use an inequality. So there's a special subset of translation questions involving linear equations, and these linear equations when you're thinking about it, I want you to think of a linear equation as an equation that can be drawn as a line in the xy coordinate plane. When we graph it, it makes a line. That's why it's called linear or linear. If we're looking at it algebraically, what it means is there are two variables, x and y. If it's an expression instead of an equation, it will often just have one variable. And neither of the variables is taken to any power other than 1. That is, they do not have any exponents, nor are either one in a denominator of a fraction. So for example, y equals x is linear. They're both to the power of 1. Y equals x squared is not linear because it's to the power of 2. 1 over x is non-linear because we have a variable in the denominator. 2x plus 3 is linear because we have x to the first power. So keep that in mind when we start to take a look at these. So when we're thinking about linear relationships, the most basic linear equation is y equals x. It's called the parent function. Now we can change all that, change different things about that. But again, you can see the most basic form. We have x to the first power, y to the first power. And when we graph that, it will make a line. Let's just investigate that graph a little bit. So I'm going to make myself a little xy coordinate plane here. I apologize for the wonkiness of it. And if I make myself a little t-chart to keep track of my x's and my y's, I'm going to use the equation y equals x. So when x is -2, if I put a -2 in for my x, I see, oh, my y is -2. Okay, -2. Put my x back there. My x is -1. Put a -1 from x. Oh, it looks like my y is -1. When my x is 0, oh, my y is 0. Wait a minute, I see a pattern here. When x is 1, y is 1. When x is 2, y is 2. When x is 3, Y is 3. Okay, let's plot these points. I'm going to go over to X is -2, down to Y is -2, and I'm going to put a point there. X is -1, Y is -1, put a point there. X is 0, Y is 0, put a point there. X is 1, Y is 1, put a point there. X is 2, Y is 2, put a point there. X is 3, Y is 3, put a point there. Oh my goodness, I could do this all day, but what shape am I making? You'll see I'm making a line, right? And why does it make a line? Well, it's because our rate of change is constant. You'll notice that every time the X goes up 1, Y goes up 1 the same amount. X goes up 1 again, Y goes up 1. X goes up 1, Y goes up 1. We're adding 1 to the Y every time the X increases. Now, does it have to be just like that? No, not always. Let's try another one. Let's try this one in purple. Okay, let's alter it a little bit and see what happens. What if I make my my equation 2x plus 3? Let's see. If I put I'm not going to do as many points on this one, but let's do -2, -1, 0, 1, and 2 and see what my y values are. Well, when I put in a -2 for my x, I'm going to do that in purple. If I put in a -2 for my x here, 2 times -2, that's -4, plus 1, that's -1. Now, if I put in a -1 for my x here, I'll get -2 plus 3, that's 1. If I put in a 0, 0 times 2, that's 0, plus 3, that's 3. Put in a 1 here, 2 times 1, that's 2, plus 3, that's 5. Go ahead and put in a 2 here, 2 times 2, that's 4, plus 3, that's 7. So let's plot those points. I have -2 on my x, -1 on my y. I have -1, 1, -1, 1. I have 0, 3, that's going to be up here. I have 1, 5, that's going to take me up 2 more points on my y-axis. Ooh, you can see I'm still making a line, right? But this line is steeper. Why is it steeper? Sorry, it's not a very good graph of a line, but you get my point. It shouldn't curve like that, of course. It should be quite a bit straighter, but I didn't make my little points equally spaced, so you'll have to bear with me. It should be a little bit straighter like this. There we go. And the reason why it's steeper is because it has a steeper slope. You'll notice here, the 2, let's see where that pops up in our points. Every time I made my x go up by 1, my y went up by 2, by 2, by 2. And that's because each time the x increases, it gets multiplied by another 2. So 2 gets added to my output, my y value. Now, something else that happened, you'll notice, is that it crossed the x-axis 3 higher. Why? Well, originally when I put in 0, I got out 0 because y equaled x. Now when I put in 0 to this guy, it came out to be 3. So it started up a little higher. So that's called our y-intercept. So you'll notice that that 3 was right here because any term that in our equation that doesn't have an x in it will be left when we make x 0. So that'll come up again for our advanced math chapter when we're talking about graphing a little bit more. But this is a very classic form of a linear equation that we have right here. It's called slope-intercept form. The general equation is y equals mx plus b, and m is our slope. It's our rate of change. It's how quickly the line is increasing. It's called our slope. The b, this guy, is our y-intercept. The y-intercept is where the line crosses the y-axis, and we'll see how that works in word problems as well. We also have the standard form, and this here works really well when we have 2 rates of change. We have a and b as our rates of change because they're both attached to our variables, and c is our total. So let's look at how this works. There are too many goats in the basement. Dad pays you a flat fee of $200 for being brave enough to go down there at all, plus $50 for every goat you catch. Write an expression for the total amount of money you'll get if you catch X goats. So let's think about this. We're going to get $200 no matter what, so we're going to put that down on the paper. But then we're going to add on to that some more money for every goat we catch. For $50 if I catch 1 goat, 50 and 50 again. If I catch 2 goats, 50 and 50 and 50 again if I catch 3 goats. So I'm going to add on 50, not just one time, but however many times the number of goats I catch. So I can put a little X here to represent the number of goats. Now, and that should equal the total amount of money I make. We'll call that Y. So let's just test this out. If my X is the number of goats and my Y is the total amount of money, if I catch 0 goats, if I put 0 into this equation, 50 times 0 is 0, and I'm still going to make my $200. My dad promised me, yes? Now, if I catch 1 goat, I should get $200 plus an extra 50. Is that what this equation says? Well, sure, it's 200 plus 50 times the 1 goat that I caught. So if I catch 1 goat, I'll have $250. If I pop in a 2 for my X, I'll do 200 plus 50 times 2. So 52 times, that's $100, and I'll get $300. We can do this all day long, but please notice, every time I catch another goat, my Y value goes up by 50, which makes sense because I'm getting $50 for each goat. So let's analyze this equation. I'm going to rewrite this as Y equals 50x plus 200. Now it looks an awful lot like an equation that we were just looking at, y equals mx plus b. We can see that the m is our slope and our b is our y-intercept. So let's think about what this means in terms of our little story here. Well, it seems that the m is how much for each one, how much per increase, right? Now, if we think about the language we often hear in school about slope, we hear about it as in change in the y value, the output, per change in the x value, right? Change in y over change in x. Sometimes you hear rise over run. Well, remember, rise, that's a change in the up and down direction, change in y's, and run is the change in the x direction. So really, we're saying the same thing. So if we're thinking about that here, the 50 would be the change in y's per change in x's. Remember, y's were our goats, and x's, y is our money, and x are our goats. So would it be fair to say that $50 is our change in goats? I keep swapping them. Change in money per change in goats? Absolutely. Every time our goats go up 1, our money goes up 50. And check it out. 50 over 1, that's 50. That's our slope. So our slope is our change in y value per change in x value, or change in money for this particular situation per change in goat. So we can always think about the slope as the rate of change, how quickly our y value is increasing for each x increase. Now, let's think about our y-intercept, this guy over here. We know that that's our y value. The y-intercept, I'm going to take this down here a little bit. The y-intercept is the y value when the x value is 0. Do you see that? That was 200 was our y value when our x value was 0. But remember, our y's are our amount of money when our x value or our goat value was 0. So basically, it's a way of saying this is our baseline. This is what we get no matter what. It's not tied to a number of goats or a rate of change. This actually is not changing at all. It's just a constant. It's just kind of sitting there in our equation. It's our given. It's our starting point. It's our baseline. So when we see a problem like this, we can think about it in that way. Now, let's look at another version of a linear equation in slope-intercept form, y equals mx plus b form. Let's see if we can look at this equation and see all the pieces, y equals mx plus b. The equation, now they're giving us a very specific one, g equals 350 minus 6h, shows you how many goats are remaining in the basement, which means g, this is the goats remaining in the basement after you work for h hours. So h represents the number of hours. They're asking us now, how many goats do you catch each hour? Well, this is interesting. Let's think about what this is saying. It says the goats that remain in the basement, they are 350 if you take away 6 for every hour that you work. So if we're reading it that way, it might be easy to see that, for each hour that I work, I'm taking away 6 goats from the basement. So that's one way to look at it. Another way would be to rewrite this in y equals mx plus b form. G equals, we're going to put our variable term first, just like we have the variable term first here, negative 6h plus b. Now let's think about it this way. The g, the goats remaining, that's my y value. Oh, sorry, should be plus, oh my goodness, plus 350 here, because that's what I have as my y-intercept, as my constant in our original equation. So let's try that again. So my g is my y value. My negative 6 is my slope. My h is my x. And my 350 is my b. So let's think about this. Because we usually think about the slope, let's talk about it first. We'll talk about our little slope guy right here. That's our negative 6. That's our m, the coefficient on our variable. We'll put it over 1 since we often think about slope as change in y over change in x. So this guy here would be our change in y values. This 1 here would be our change in x values. Now remember, our y values here, our y values are represented by a g now. So that's the goats remaining. So the change in, we can even just say instead of y, change in goats remaining. And our x, remember our x is now represented by an h. An h, that's the number of hours. So I can even cross out that x there and say hours. So we can say that the number of goats remaining goes down 6 every time the change in hours goes up 1, because it's a positive 1. So the goats go down 6 every time the hours go up 1, meaning for every hour you work, the goats remaining decrease by 6. And why? That's because you're catching 6 goats each hour. Now let's just for fun think about what the 350 is there for. You know what, let me color code this for us. Let's make it light blue. 350. Well, that's our y-intercept. That's our base rate. That's our starting amount. So let's think about what this would be if I have, I'm just going to write it out one more time, g equals negative 6h plus 350 if my h was 0. Well, if my h is 0, making a little t-chart, if my h is 0, my number of goats remaining is 350. So after 0 hours of work, there are 350 goats in there, meaning before I started working at all, there were 350 goats in the basement. So 350, as we said before, it's our y-intercept, it's our base, it's our starting. All right, let's practice some of these. So Freddie bought a flower for his garden. The equation h equals 2.5d plus 12 models the height h in inches of the flower d days after he purchased it. How much does the plant grow in inches every day? The key here is the every day. So when we look at this equation, remember we have h equals 2.5d plus 12. 12 is our starting point. That's our height when the number of days is 0. So that's our starting height. How much are we adding on to the height for each increase in the day? We're adding on 2.5. So every time our d increases by 1, our h increases by 2.5. Don't believe me? Let's make a t-chart. Inputting a d, getting out an h. When I put in 0 for d, I get out 12 for h. On day 0, my height is 12. When I put in 1 for my d, boopity-boo into the calculator, you get 14.5 as your height. Put in a 2, you'll get out 2.5 more than that, which will be 17. put in a 3. You'll get out 3 times 2.5, which is going to be 7.5 plus 12. That's going to be 19.5. So you can see for each increase in your day, we add another 2.5 to the height. That's our slope. Remember, our slope is a change in height per change in day, our change in y per change in x. So our answer to this one will be 2.5. Let's read question number 2. It says, make this a little smaller, give us some space. Sophie runs a lemonade stand and puts the money she makes in her piggy bank. This is modeled by the equation P equals 2L plus 14, where P is the amount of money in dollars in her bank and L is the number of cups of lemonade she has sold. How much money in dollars does Sophie get for each cup of lemonade? If you're ever having trouble understanding these problems, I highly recommend writing down the equation on your scratch paper and labeling all the pieces. So we have our P. This is the amount of money in her piggy bank. L is the number of cups of lemonade she's sold. And remember, our 2 is our rate of change. I'm going to introduce you to this symbol delta. Delta means change in Greek. Well, it's a Greek symbol for change in. So that would be the change in money per change in lemonade cups. Yeah, and this is our starting point. This is our money when our lemonade cups are 0. So if they ask us how many does she get for each cup, well, we know we start out with 14 already when our L is 0. So 14 is our baseline. That's not what we're looking for. We want how much we add to our baseline every time we increase our number of cups lemonade by 1. So again, the lemonade number of cups is tied to the 2. So as I increase the cups, it'll affect our equation by 2. So every time we increase our cups by 1, we're increasing our money by 2. So our slope is what they're asking us for here, and the answer is 2. Lana got a box of donuts. The equation D equals 120 minus 5/8 shows the number of donuts. D for donuts. D, remaining in the box, so remaining in the box after H hours. How many donuts were originally in the box? So originally means how much were in there after 0 hours. Think about popping in a 0 for your H. You'd get D equals 120 minus 0, or 120. They're asking us for the original amount, how much we started with before we started adding some hours in there. So our answer will be 120, our baseline, our y-intercept. So let's see another one here. The equation C equals 0.1m plus 0.15t plus 50 shows the total cost C in dollars of Glenda's mobile phone service each month, where M is the number of minutes of phone calls, T is the number of messages she sent. How much is Glenda charged each month in dollars for each text message? This is for each text message. Well, the text messages, you'll see, are tied to the 0.15. So every time T goes up by 1, I add another 0.15 to my total cost. So for each text message, it would be $0.15 or 15 cents. Andrew spent 1 day building a wall in his backyard and has added to it every week since. The equation B equals 25 times quantity W plus 10 models the total number of bricks in the wall W after he started. How many bricks did he put in the wall on the first day? So if we think about this, W is the weeks after he started. So what would be our baseline? What would be what we had there on the first day when our weeks are 0? This right here is not in y equals mx plus b form, but we could distribute the 25 and see it looks like this. What's our y-intercept? 250. That's our b value, our brick value when our W is 0. So we can see that the answer to this question is our starting point, 250, our y-intercept, our baseline, what we had on there before we started adding 25 every time our week goes up. All right, so let's talk a little bit about the relationship between slope-intercept form, the form we've been working with, and standard form. So standard form, if we'll remember from before, we have ax plus by equals c, equals a constant. Yes? If that's the case and we want to solve for y, we would just take our ax plus by equals c. We'd subtract ax from both sides. We'll get by equals negative ax plus c. We'll divide everything by b. And we'll cancel out the b here. And we'll get that y equals negative a over bx plus c over b. So what you can see here, if I write the y equals mx plus b form underneath, is that we can turn one into the other. And if I'm looking at standard form, a negative a over b, see the coefficients on the x and the y, are our slope. And c over b, that's our y-intercept. So these forms are useful because they describe different situations. But if you want to get, say, the slope out of standard form, please don't think of it as a, just the coefficient on x. That only works if it's in y equals mx plus b form. So we would have to solve for y to find the slope, which comes out to be negative the coefficient on the a divided by the coefficient on the y. Or sorry, negative the coefficient on the x divided by the coefficient on the y. And the y-intercept, again, don't just think it's c, it's not. It's not just the constant, it's the constant divided by the coefficient on the y. We'll see more when this will be helpful a little bit later. But let's try something. Let's try setting up some equations now. We're going to first try one in slope-intercept form, and then we'll try one in standard form so we can see why we have two forms of the linear equation to begin with. So this says a car with a price of $17,000 is to be purchased with an initial payment of $5,000 and monthly payments of $240. Which of the following equations can be used to find the number of monthly payments M required to complete the purchase, assuming there are no taxes or fees, meaning there's nothing else to worry about? So let's make an equation. Yes, they didn't give the following equation, so we could set it up. This is really great for slope-intercept form, y equals mx plus b form, because we have a certain amount that we paid initially. We have an initial payment of $5,000. That's our starting point. That's our baseline. That's going to go in for our y-intercept. We also have something that varies, meaning every month, the more months I do, the more money I add. There's an amount of money that's tied to a variable number of months. That's our slope. This is how much we pay for each month. Now for each month, that's going to be our x. And then the total amount of money I get from doing all that, putting in the base amount and then paying $240 for each month. In fact, that'll be our M for our month. That would equal the total amount of money I have to pay for the car. That's going to be the total amount of the car's price. So let's pop this into the equation. My total amount was $17,000, and that's made up of the $5,000 I put in initially plus $240 times the number of months that I'm putting it in. So now we can solve for M here if we wanted to find the number of months it would take us to pay up to the total amount of money. So you can see here, this follows very closely the y equals mx plus b format. Now let's see one in standard form. So remember, our standard form is ax plus by equals c. So this says a concession stand at a high school baseball game sold peanuts for $2.50 each and hot dogs for $3 each. If the concession stand brought in $196 or made $196 and sold 42 hot dogs, how many bags of peanuts did the concession stand sell? Well, if you think about it, the total amount of money we're going to make is going to be made up of two smaller subtotals. So we can think about it in the same way. So if we think about our C, our constant, as the total amount of money that we're going to make, It's made by adding the subtotal, the money made from the hot dogs, to the money made by selling the peanuts, right? If we add those monies together, we'll get the total amount of money, right? But the amount of money we make from the hot dogs is based on how much we're selling the hot dogs for. Let's start with the peanuts actually here. Let me swap these guys. The question says peanuts first, so let's put the peanuts first. A little less confusing here. The amount of money we make on the peanuts, wow, could I have written that worse? Peanuts. The amount of money we make on the peanuts is made by multiplying how much for one peanut situation, 250, times the number of peanuts. Let's call that P, the number of peanuts, right? And then the amount of amount of money we make on hot dogs is made by multiplying the amount of money for one hot dog, $3, times the number of hot dogs, 42. And then if I add those together, I'll get the total amount of money we made that day. So you can see here how this pattern follows the standard form of the linear equation. We have our subtotal, that's our AX, how much for one times the number. And then we have the subtotal BY, that's again how much for one, that's how many we're buying, and that gives us the subtotal. If we add all that together, we get our total, our grand total. Yes? So if we're thinking about it this way, now we have an equation that we can solve for how many bags of peanuts we sold, right? We'd have 250p plus 3 times 42 equals 196. So again, we could solve that for P. We're not going to do that right here, but because we did a lot of solving equations before. But the idea here is to notice that this one has 2 rates of change. The more peanuts I sell, my total goes up by 250. The more hot dogs I sell, my total goes up by 3. We have 2 rates of change and 2 sets of numbers that are attached to it, 2 sets of variables that are attached to it. Now here's something funky that doesn't appear to be either one, but if we use our translation system on this, it works really well. It says the width of a rectangular vegetable garden is W feet. So let's draw ourselves a little rectangular vegetable garden. Okay, and we're gonna make the width W feet. I always make the width the smaller one, unless it says otherwise. The length of the garden, we'll call that L, is 8 feet longer than the width. So the L is whatever the width is increased by 8. Which of the following expressions is the perimeter in feet of the vegetable garden in terms of W? So in terms of W means we're going to use W to set this up, but we know our perimeter is all the sides added together. It'll be this side, which is the same as its opposite side, so it's W, and this side, which is the same as its opposite side, which is W plus 8. If we add all those guys together, the perimeter would be W plus 8 plus W plus W plus 8. If we combine our like terms, 1, 2, 3, 4 W's, that'll give me a perimeter is 4W, plus, let's combine our constant terms here, 8 and 8, plus 16. And that would be our perimeter. Oh, wait a minute. Does that not look a little bit like a linear equation? It does. First of all, we have all our variables to the first power. We have something that's in the place of the slope and something that's in the place of our constant. Amazing. So let's think about understanding a linear equation we didn't have to make ourselves, a little bit like we were doing in that first drill. So let's take a look at this. A team of workers has been moving cargo off a ship. Wait a minute. This sounds a little bit like removing goats from a basement or taking donuts out of the box, right? The equation below models the approximate number of tons of cargo Y that remain to be moved after X hours after the team started working. Y equals 120 minus 25X. The graph of this equation, the XY plane, is a line. Shocker, right? It's linear. It looks like that. There's X and Y to the first power. What is the best interpretation of the X-intercept in this context? So let's remember, the X-intercept is where the line crosses the X-axis. So just to get really clear on what this is, the X-intercept is where the line crosses the X-axis. That's going to be right here, right? What do we know about the X-intercept, even if we have no values at all? That if it touches the X-axis, the Y value is 0. Right? That's where the y value is 0. So if we think about it in this context, the y's represent the tons of cargo that remain, right? That's our y value. When our y value is 0, how much cargo remains? 0 cargo remains. No cargo is remaining. So they're asking us about what the x-intercept represents. Well, it's the x value where the y value is 0. So, actually, let me color code that. Let's make that the x value is what we're looking for where the y value is 0. Or in this situation, the hours value where the tons of cargo value is 0. What do you think that means? Well, it means that's the amount of hours. We're looking for hours because we're looking for an x value, right? We're looking for the x-intercepts. That's an x value. We're looking for a number of hours that would make no cargo remaining. So basically, how many hours it takes to remove all the cargo. Well, let's try that out. We have our equation, y equals 120 minus 25x. Let's put a 0 in for our y value. Let's solve now. We get negative 125 equals negative 25x. Oops, sorry, that was a 120, not a 125. There we go. Divide by negative 25 on both sides to isolate our x value. And we get that x equals positive 4.8, which means the number of hours is 4.8 to make the y value, or the tons of cargo that remain, 0. So this point that we're looking at right here is actually not here at all because we are, because it's a positive number, right? So let me actually grab that point and make it so it looks a little bit better for us. Let's see, it would actually be probably over here. Well, if we're looking at this graphically, it'll have a negative slope and a positive y-intercept. So we're probably looking at something that looks a little bit more like this. Nonetheless, we are still looking at the x value that gave us a y value of 0. It just happened to be 4.8 hours that would give us no cargo remaining. So let's see which answer choice says something like that. The team will have moved all the cargo in 4.8 hours. That sounds promising. None remaining, and the hours are 4.8. And again, we are looking for the x value, so we're looking for the 4.8 for the hours value. This says 4.8 tons of cargo. The team has been moving about 4.8 tons of cargo per hour. Oh, no. We got to get rid of that one because the 4.8 is the hours. How much cargo is it moving per hour if x is hours? It's moving 25 per hour. It's taking 25 away each time the x increases. C says the team has been moving 25 tons of cargo per hour. This is true, but it's not the meaning of the x-intercept, so that's not our answer. D says the team started with 120 tons of cargo to move. This is true. That's our y-intercept. That's what we started with, but that is not the answer to the question of what the x-intercept is. That's the y-intercept, so we can cross that out. All right. So the most important things to take away from this conversation for the meanings of each piece of the equation, right? If we have y equals mx plus b, the slope is the change in y values per change in x values. The y-intercept, that's our b, that's the y value when the x value is 0. The x-intercept isn't a constant here, but if you solve for the x value when the y value is 0, you'll get the x-intercept. The coordinate pair x and y, these guys here, or you can say x and f of x, or when f of x equals y, it's basically the y value is y when the x value is x. So just to give an example of that last one, if I say, let's use the flower example we had before, that the height of the flower is 2.5 times the number of weeks it's been alive plus 14. Yes? So this is W is for weeks, and this is the height of the flower. If they asked you, and I'm going to make this now x and y so we can use it as x and y. If they asked you what is the meaning of the point I don't know, 219, what we would be able to say is, well, X, this is our X value, this is our Y value, this is the number of weeks when our Y value or height was 19. We'd say on week 2, the height was 19. That's the meaning of that point. So again, when they ask for the x-intercept in that last problem, the x-intercept is the x value where y is 0. In the problem we just looked at, in that equation, x is the hour and y is the tons of cargo. You can even just take the sentence that we just looked at and swap out x for tons of cargo and y, swap out hours for the x and tons of cargo for the y, and we get this sentence: the x-intercept is the hours value where the tons of cargo is 0. So let's look at it again when we see that. Yes, we have that same problem. So again, what is the interpretation of the x-intercept? We know to call the x-intercept the x value where the y value is 0. So literally take this equation now, and instead of saying x, say hours. We're going to swap out that x for hours. It's the hours value where the y, well, we know that y is the tons of cargo that remain. We'll swap out y with tons of cargo remaining is 0. So we're looking for the hours value where the tons of cargo remaining are 0. We just have to find which answer choice says that. All the cargo is moved, right? That's the only one that says something like that. So let's try another. This says the boiling point of water at sea level is 212 degrees Fahrenheit. For every 550 feet above sea level, the boiling point of water is lowered about 1 degree Fahrenheit. Which of the following equations can be used to find the boiling point B of water in degrees Fahrenheit, x feet above sea level? So let's think about what's going on here, right? Let's just make a little T-chart for a second. We know where we're starting at, right? At sea level, remember, if x is our feet above sea level, x, let me color code this for us. If our x is feet above sea level and our B is going to be the boiling point, well, let's think about this. When we're at sea level, our feet above sea level is 0. Our boiling point is 212. And it says for every increase of 550 above sea level, so if I increase 0 by 550 and get 550, my boiling point will lower by 1 degree Fahrenheit, so it'll be 211. If I increase it again, I'll get 1,100 feet. And then I'll lower it again. I'll get 210 as my boiling point. So if this is the case, we have something very interesting going on. I can just try these out in the equations and see which one works. Which one do I put in a 0 and get out 212? If I put in a 0 here, I get 550. So that's not my answer. If I put in a 0 here, I also get 550. That's not my answer. If I put in a 0 here, I do get 212. And if I put in a 0 here, I do get 212. So those can stay in. Now let's put in 550 and see which one gives me 211. If I put in 550 here, it looks like it would be 212 plus 1. No, that's not 211. Here, if I put in 550, it's 212 minus 1. And that is 210, so that should be my answer. Now let's analyze this a little bit more. I'm going to write this in y equals mx plus b form. 212 minus 1 over 550x. And I'm going to swap these around so it looks a little more like y equals mx plus b. Y minus 1 over 550x plus 212. Well, it did tell us that our starting point was 212, so we would definitely want that to be our y-intercept. We would want that to be our number without the variable on it, right? We also did see, I'm going to put this negative in the numerator so you can really see it, that this would be our change in y. That's our change in y, which is our change in boiling point. And this would be our change in X. That's our change in the feet above sea level. So we can see the temperature goes down, the boiling point goes down 1 every time our our feet above sea level rather, goes up 550. So this is definitely something that reflects the situation that we're looking at here. And again, that just means swapping out our B for our thoughts of Y, and our X can stay our X.